Hello, everyone. We're very excited to start our session 7 with Peteris. Thanks a lot for everyone to join in. And we're very excited for Peteris to let us know about fully automated yield aggregation. And it's already been our session 7, have been in various different cities, and I'm very excited to start today's and this week's session with Peteris. So the floor is yours, and thanks a lot, Peteris, for helping us.
Yeah, awesome to be here. Thanks for hosting me. Excited to get into the topic. So today I'll talk about fully automated yield aggregation, which is going to be kind of a very specific use case example, but really illustrating a much broader principle of like how we can try to build more trustless smart contracts, more trustless protocols, and specifically also kind of taking using some advantages of StarkNet. Okay, trying to show my screen. Let me know if you can see the slides. Okay. Yeah, so kind of 3 objectives for today. One is going to be, I'll quickly introduce Yagi and explain kind of our focus on trustless yield aggregation and what we're trying to achieve. I'll talk about the importance of trustless systems in general and why, in crypto, we should strive to try and build trustless systems where possible. And also talk about, with practical examples, right? How do we build trustless systems and how we think about building trustless systems, and kind of use the example of trustless vaults, and then trustless yield aggregation really is kind of an organizing application of that. And really, these use cases are chosen because they, traditionally, if we look at how they're being solved on mainnet or other networks today, they really are not trustless. So I think it provides a greater challenge, and as you'll see, the sort of the design space really opens up when you try to tackle these more challenging use cases. So what is Yagi? We have kind of 2 main products. We have Yagi Automation, which is a keeper network on StarkNet. Effectively, what it allows you to do is, if you're a smart contract developer, it allows you to automate transactions that call your smart contract to perform some sort of maintenance, upkeep, or other types of tasks on a regular or custom schedule specified by yourself. So kind of illustrate the need for that. Let's say you have a contract that needs to be called every single day to do some sort of update. One way to do that would be to actually manually make the transaction, right, using your wallet. The problem is, if you want to go on holiday, or if you fall ill, how can your users trust that you're going to actually make that happen? And it's also just inconvenient, right? So your second thought may be, hey, maybe I'll write a bot that will make that call on a regular basis, right? And then you're maintaining this kind of additional piece of infrastructure off chain that people have to rely upon, right? So if the server goes down or something happens, maybe that transaction is not getting called. And the other kind of problem, is really it's just extra effort, right? You just have to put in all this work now to maintain this kind of additional piece of DevOps infrastructure. But as Cairo developers, we really want to focus on just the smart contract development, right? That's what we enjoy. So that's where Yagi Automation comes in. It's a way to specify a task and then say in your smart contract when it needs to be called and how, and then we sort of provide a network of keepers of bots that actually guarantee that these transactions happen and that your contract gets called. And the nice thing is that A, you don't have to write all this extra infrastructure, and then B, you also get sort of better and better guarantees over time that those transactions will get executed, and your users get ultimately better guarantees over time. And then the second product is Yagi Vaults. It's more recent, and so the idea is really building different kinds of investment strategies. So where you can deposit a single token, let's say it's Ether or DAI or another type of token, and we try and curate investment strategies and develop investment strategies that basically allow you to compound some of that token, right, or get exposure to different types of yields that are available in the StarkNet ecosystem. And then both applications are developed, and deployed on testnet and available right now, so you can definitely check them out. One thing we're doing with the vaults is we're going to be starting to combine kind of our own vaults and also curating third-party vaults. And really, what that is enabled by is that we use a single consistent standard, which is called ERC 4626, for these vaults, making them kind of very composable. and making it easy to sort of use the same tools, infrastructure, user interface across all of them. So we've also shared that openly. So if you want to check it out, it's one of our kind of open source projects, which is the ERC4626 vault template, used in all our vaults, but also other people are looking to kind of incorporate it in sort of gaming and DeFi vaults going forward. So very, very excited to continue to push that forward. We've right now are integrated with a couple of different protocols. So automation is used by, the ISA game by Topology, will be familiar to everyone here, I'm sure. And then also the multiplexer wallet. I can see Sammy in the audience here. Also an awesome use case of basically splitting up different transactions on behalf of users. And then in progress with Vistrali and a couple other teams as well. And then vaults, we're building on top of several kind of protocols on StarkNet. The first one was built on top of Xbank. We'll talk about a JediSwap vault here. And we're also, building on top of Mammoth, which is a Zigzag protocol. And so there's also, some smaller protocols that we're starting to integrate, such as oracles and so on, which I'll also talk about. So yeah. So in terms of like what we're trying to do here is we're really trying to build two things. We're trying to build, first of all, trustless vaults, which, as I've described, are really investment strategies that target a single type of token. And then the second thing is we're trying to create a trustless yield aggregation. So what does that mean? Yield aggregation simply means that instead of you coming to Yagi and saying, hey, I have some Ether, I'm going to invest in this specific strategy, you could just come with your Ether and basically deploy it and let us sort of automatically decide where that gets allocated, right? And so traditionally, people have tackled it through this kind of community multi-sig approach, where there's a multi-sig of strategists or protocol administrators that effectively make those decisions on behalf of users that basically decide, hey, we think this vault is going to perform better, and so that's where your money is going to go. We are not aiming to create an asset management company. We're not aiming to recruit people to make investment decisions with your money. We're sort of really excited about seeing what we can do just purely with code. And so we're really trying to do trustless vaults that have really automated strategies, and then also trustless yield aggregation. So allowing you to come with a single token and basically sort of automatically be reallocated to the best vaults possible, right? And these are really challenging things to do, which we'll talk through how we try and do that. But before, let's make sure we all agree on kind of what trustless is and kind of talk a little bit about the design space, because there's things we may not cover today. I mean, ultimately, trustlessness means we do not need to trust a third party, right? Kind of similar terms are being thrown around: permissionless, decentralized. They're slightly different. So when we say permissionless, it really means that anyone can use with a protocol. With a trustless protocol, it doesn't necessarily need to be permissionless. And then also, although commonly they are, and then you have sort of decentralized, which really means distributed control. And we'll see that decentralized actually is maybe a subset of trustlessness, and it's not always trustless either. And so, yeah, important not to get these terms confused. Why does trustlessness matter, though? Well, I think first and foremost, it's just philosophically aligned with the formation of the field, right? I mean, it's almost, cryptocurrency exists because we wanted to have this property of trustlessness, right? Arising kind of from some of the things that we didn't really enjoy in terms of how the traditional finance world was handling the financial crisis and the aftermath of that. That became kind of the foundation of Bitcoin, and so I think it's important that we do look back at those principles and try to implement them. The very related thing is that trustless protocols are uncensorable, right? If they're developed in the right way, it's very hard for an entity, kind of almost by definition, to block the protocol from existing. The third one is very practical for developers. It's I think minimizing regulatory impact. We're kind of entering in an environment where there is more regulatory tension around crypto, partially because it's becoming more successful. And so I think trustlessness is a great way to minimize the impact of that. And really, by building trustless protocols, they're a lot simpler to regulate, and often, there isn't that sort of discretionary management element or discretionary administrative control that would require it to be marked as something that needs a lot of oversight. But please consult your lawyers on this. And this is very much an evolving field. Finally, from a kind of infrastructure perspective, I think they tend to be easier to work with, and especially in composition. Because ultimately, trustless protocols, tend to be available on chain. You don't have these kind of off-chain computational elements you may have in non-trustless protocols. You don't have to really simulate kind of untrusted third parties. So you can use on-chain tooling very often to mock contracts. And so it's much easier if you are a trustless protocol working with other trustless protocols to really do very effective integration testing and see what would happen, because you don't really have to model all these kind of off-chain components in there. It is challenging though to build trustless protocols, and I'm sure you'll be more convinced about that as we go on through this one use case. It does need a bit more creativity in the design stage of the protocol, right? Often where you would stop and say, hey, we'll just kind of manage this ourselves, you have to go a step further and say, no, how do we make this step trustless? Second, it's difficult to use certain contracts, namely upgradable contracts, right? They're kind of not trustless by definition. If there's a certain person that's kind of authorized to upgrade a contract or a certain multi-sig, it just sometimes means that you have less contracts to work with and less integrations to make. But of course, the flip side of that is that if you're trustless, you will have more protocols that will want to build on top of you, because it's easier to reason about what can happen with your protocol. So that's a trade-off. It's also harder to protect against MEV. So MEV is when there's some arbitrage available, and so through the kind of the way you develop trustless protocols, you typically end up in situations where it's just more predictable what the protocol would do, because you're not relying on off-chain entities making decisions. And when it's more predictable, it also means that these transactions can be front-run. And so it's very important that we kind of think extra hard about how we protect against MEV. And finally, smart contract vulnerabilities can be more costly with trustless protocols, right? If the protocol is like more immutable, it means that if something goes wrong, there's really no way to fix it, right? Because we don't have this upgradability element, there's no way to really step in and fix the protocol, right? And we'll see that this is true with different expressions of trustlessness. Okay, so let's kind of give some examples of what protocols can aim to be trustless. There's sort of three main categories, and the way I've kind of split them up here is really looking at what the off-chain operators are doing, right? And when I say off-chain operator, I mean a human or a human-operated service, right? It could also be like a bot or an MEV bot or a trading bot operated by a human, also counts as an off-chain operator. A keeper also could be an off-chain operator. So the three categories are, one would be, maybe I'll start from the right-hand side, because those are, I would say, the most difficult to make trustless. And then we'll kind of move to the left and we'll see what the gold standard is for trustlessness. So there's something called, that I try and call a robust incentive network. I don't know a more formal name for it, but this would be a situation where we have some off-chain operators, but the network incentives are set up in a way that the damage that they can do to the protocol is very limited, right? So one example of this could be that there is an economic consequence to some off-chain operator producing the wrong action, right? So this is what, if you're familiar with token curated registries that aim to sort of curate a list of things by creating an incentive system, that's what it aims to be. I think prediction markets are also one example of robust incentive networks, right? If you're participating in a prediction market and you're making a prediction, you typically have to stake some money on that prediction be correct. So it gets more expensive to manipulate the prediction, and so on and so forth. These are really hard to design, and I think we have seen very few really successful and truly trustless implementations of robust incentive networks, but I think they're a very viable path forward. The more common one we've seen a lot is just DAOs, right? Where you have many off-chain operators, right? And so the way DAOs work is they sort of put everything behind a governance vote, right? And we'll just basically say, hey, as long as we trust that this token is distributed across many participants and this voting power is distributed, well, then we can make any type of decision, and we're sure that it's very economically expensive to sort of buy enough of the token to really manipulate this decision, right? And that's kind of the core principle behind DAOs. The problem in practice, and this is why most DAOs aren't trustless, is that, and this is also why, if we ask you the question, are governments truly trustless, right? Are even democratic governments truly trustless? Well, it sort of depends on what you're looking at. If you're looking at a very specific part of the government, there's usually people that are employed to do a specific duty. And in that moment where they have that role and they're playing that role, they're a person that needs to be trusted, right? And so in many cases with DAOs, it's the same sort of thing where DAOs will elect multi-sigs, they will elect different contractors, and then basically, sure, there was a vote at some point that elected that multi-sig and elected that contractor, but it doesn't mean that the protocols that they then produce are trustless, right? If they're managed in that way. So this is something where it definitely falls on a spectrum of trustlessness, right? And this is not even mentioning kind of the challenges of guaranteeing that it's very expensive to actually do a governance attack and so forth. So what is the gold standard? Well, the gold standard, I think, is when you have absolutely no off-chain operators at the kind of your core protocol level, and it's not always achievable, of course. And that means your protocol will be fully automated and fully immutable, and nobody can change it apart from maybe some parameters. And sort of another name for this is kind of commonly been used is called hyperstructures. I think hyperstructures actually have a more specific definition, which I'll cover. But basically, if you have no off-chain operators and no kind of administrator, there's no owner to the contract, really, you can pretty much just read the code and understand what the contract does, right? And that ultimately is, I think, the most trustless implementation that we can aspire to get. And that's where we're focusing most of our attention, at least when it comes to the vaults. We're really trying to be in this like left-hand bucket and trying to see if we can make protocols that kind of all the magic is written in the code itself, rather than relying on some external party coming in and doing the work. Okay, so hyperstructures, what is this term? If some of you may be familiar with it, this came out of the development of the Zor protocol. The idea is that hyperstructure is a crypto protocol that can run for free and forever without maintenance, interruption, or intermediaries, right? So we're seeing the trustlessness part there. But there's also a couple of other elements. So for example, hyperstructures are more opinionated about things like being free and having zero fees. They're opinionated about them being expansive and having some incentives for other people to integrate with hyperstructures. So it's a bit more of a niche definition. If you haven't read the essay on hyperstructures by Jacob Horn, who came up with the concept, I encourage you to do so. It's a wonderful essay. And will definitely kind of inspire you in how you think about protocol design. But yeah, not every trustless protocol needs to be a hyperstructure, I think. However, I think it's hyperstructures are one of the most excellent templates to strive for where possible. Okay, so we'll try and tackle and go through a specific example. So let's try and build a trustless vault. And specifically, we'll look at building a vault on top of JediSwap. And specifically on top of a JediSwap ETH DAI liquidity pool, right? So kind of brief recap on JediSwap. It's an automated market maker. It means that it's an exchange that operates fully autonomously. You have these liquidity pools, for example, in this case, Ether and DAI pool that allows users to come in and trade Ether for DAI and vice versa. And how can they do that when there's sort of no central entity kind of providing the capital? Well, the protocol kind of incentivizes people to come in and become liquidity providers. So they come in and they deposit some amount of Ether and some amount of DAI, and then they're effectively they're basically funding the exchange, and they're getting fees on the trading volume. So that gives us an opportunity to build a vault, right? What if we could build a vault on top of JediSwap that allows people to deposit both tokens basically and become a liquidity provider? In our vaults, we always like to build vaults that have a single depositor token so that they're compatible with the ERC 4626 standard. So this is what we'll try and do. We'll try and see if we can build a vault where we have actually two vaults that depositing into the same pool. One side which will deposit Ether, and another side which will deposit DAI. And if you may have heard these kind of under terms, single-sided liquidity provision or joint liquidity provision, that's exactly what we're going to be talking about today. And we'll try and push the envelope on how these are designed. So kind of brief recap on what we'll need to make this work. You may have this question of like, well, if we're depositing ETH and DAI, as a liquidity provider, typically we then own the whole liquidity share, right? So what if now we have one person depositing the Ether side and then one person depositing the DAI side? Who's going to own the actual liquidity share, right? How does that work? So we're going to borrow this principle from automated market makers, which is that when you're in a liquidity pool, the liquidity pool always thinks that both assets have the same value. This is true in sort of any Uniswap style automated market maker with a 50% weight. You can think of it basically as an index fund, which is like always perfectly rebalanced. And so it almost guarantees to us that as long as we're happy that the spot price that the market maker is quoting, the automated market maker, which just means the rate that you can exchange Ether and DAI at, as long as we're happy with that price, that means that we know there's equal value in Ether and in DAI in the pool, which means that we can, give that value back to the original owner. So basically, if I'm sort of pairing up with another person, if I'm depositing, 2 ETH in a pool, they're depositing 2,000 DAI in a pool. If that's roughly equal value, something happens, the sort of the liquidity share earns some fees. We can always just give me back the ETH portion and give the other person back the DAI portion, and we'll be roughly fine. Actually, we'll both probably be earning fees. So this is kind of a core principle that is rested upon mathematically. And actually, when it comes to design, really that's why we have this sort of custodian contract, right? This custodian contract is going to kind of hold the liquidity shares and then deposit into JediSwap. So kind of to recap, basically, we have 2 vaults, ETH vault, DAI vault. One allows people to deposit Ether, another one allows people to deposit DAI. That goes into the custodian, which then handles the purchasing and minting and redeeming of shares from JediSwap, basically. Okay, so let's try a very naive implementation, right? So why don't we just say, hey, every time that there's a deposit being made, we're going to just mint some liquidity shares. So let's say I deposit Ether. Well, there's no DAI, so nothing happens. Then somebody else comes along, they deposit some DAI. Okay, now we have a bit of Ether, we have a bit of DAI, we can mint a liquidity share, right? Okay, cool. So let's say we mint a liquidity share, somebody else comes along and provides even more Ether, and then somebody else comes along and provides even more DAI, we can mint another liquidity share, and so on and so forth. And if somebody comes along and wants to redeem some money, well, we can just burn the liquidity share and get the sort of underlying components back. So kind of seems like it should work, but there is a problem. And the problem is griefing. The problem is that these liquidity pools in certain conditions, the spot price, or we call the exchange rate between Ether and DAI, can change. And it's actually very easy to manipulate. So what could happen is that, let's say, you and I come in and we purchase some shares together in these vaults, and we're happy with the spot price. But then somebody else comes in and manipulates the spot price and then also does some more minting. Now they're buying shares that may not be good to own. And because we're all participants in these vaults, we basically all inherit these same purchasing decisions. So now we're all suffering from kind of the decisions made by future depositors, which is a bad thing. And really the core problem here is that we should not allow users to control when these shares are minted and to control the spot prices at which they are minted. And actually, if you look at how AMMs are designed, they always allow users to set some thresholds on sort of the quantity and the exchange rates of different assets, right? You should, if you're depositing liquidity, you should never just accept whatever spot price is there. You should always look and check, do I really feel that this market price is correct? Because otherwise you'll run into a problem called impermanent loss, which I won't dive into, but there's sort of another great topic to read up on. Okay, so we can fix that. We can fix that by saying, well, we're not going to allow users to determine when these shares are minted. We're just going to automate that process, right? So we're going to have the custodian do that, and we're going to have it, be done on a very regular interval. So we're going to add a keeper. In this case, we can add a Yagi keeper as an example, and the Yagi keeper will just come in every epoch, and we can define some epoch period. Say let's say a month, and then it will simply trigger the liquidity share purchasing. Every month on behalf of the vault, right? Because we now move to this epoch model, we'll also have to, say, okay, users are going to deposit their funds kind of at the beginning of the epoch, and then they can withdraw the funds at the end of the epoch, right? So there's going to be this sort of participation window that people can come in, but that's okay. And the most important thing is that now we control when the actual shares are purchased. So, is this good enough? Well, it fixes some problems, but introduces others. So the problem is MEV. And the real problem here is that the purchasing can still be front-run by bots. Even though we control when the purchasing happens, the actual purchase price can still be manipulated, right? So for example, if we were, the keeper is, scheduling a certain transaction, and then somebody's able to get their transaction ahead of that. Currently not possible on StarkNet, but who knows in the future. Always good to think about these things ahead of time. They could, for example, start buying a lot of ETH from the vault, and then that would mean that the ETH price, a lot of ETH from the underlying JediSwap pool, then the pool would quote a much higher Ether price, and we may suffer impermanent loss as liquidity share owner. So that's a problem. Okay, we can fix it. We can use a price oracle, right? If we use, say, an empiric price oracle, we get the price for Ether, we get the price for DAI. We can now say, well, do we actually believe that this price that the liquidity pool is quoting us is within kind of meaningful market bounds, right? And so if it isn't, we're not gonna make that purchase. We're just gonna wait until it is, right? So the keeper is gonna attempt to make that purchase. If it fails, it's gonna try again the next block, try again the next block, until finally the prices are in line and we think we're getting a fair price for everybody who's participating in the vaults. So caveat here, if you're carefully watching, you'll realize, hey, we're sort of introducing two new services here, right? We're introducing the keeper network and we're introducing the price oracle. How do we make sure that those are trustless? And of course, this is a very important piece. We need to make sure that, if we want to call our own protocol trustless, we want to make sure that we're integrating only with other protocols that are either trustless or they are on the path of sort of getting there. And so I think, the minimum requirement here is that both of these become, I think robust incentive networks probably is the most likely, case for both those protocols actually in the future, or minimally DAO. Okay, so does this fix it? Well, there's some minor things we need to make sure, because again, now that we're aware that we have these kind of other protocols that we need to think about, let's really think about what we're kind of how much we're trusting these protocols. So what if the price oracle quotes us the wrong price, right? That's maybe another issue. So oracle reliability is a potential problem here, right? Oracle price could be ambiguous, right? There could be adverse market conditions and people are submitting prices that they think are good, but maybe just very off or maybe very different. And so in that case, do we really want to be purchasing these shares when we really have very significant price uncertainty? Probably not. Probably we want to revert that transaction. So actually, let's add an Oracle price validity check, right? That's something people do on mainnet. We should do it too. So we'll check the Oracle price, but we'll also check the Oracle price reliability. And the cool thing is the Empiric team are building in various features for that, right? They're building in ways to sort of see how many people submitted the price, when it was submitted, and also more advanced features such as volatility oracles and things like that we can really use to make sure that the price is robust. And I think using as many of those as possible is definitely a good idea in this case. Okay, so we can kind of build some trust around using this oracle correctly. Does this fix everything? Well, there's still one more thing, which is what if there's unallocated capital, right? So what if the vault, for some reason, it's just much more attractive to people depositing Ether than to people depositing DAI? What will actually then happen is somebody will deposit, people deposit up to 1 million Ether, maybe somebody will deposit $200,000 worth of DAI. Well, the problem is 80% of that Ether depositor capital will just sit unused. So they'll be participating in this liquidity vault, but they will be mainly unallocated. So until they're finally waiting for kind of other people to appear on the DAI side. So we have this kind of balancing issue here, which is that ETH and DAI they're added in equal value terms. And either of those sides could be significantly unallocated. So this is a really hard one to fix. In practice, there's one way to introduce some asymmetry in terms of how these vaults are created. So we can start there. We can start by saying, let's add a dynamic premium. And so we'll say is we have this moment where both these vault sides were equal, where the ETH vault and DAI vault work the same, and we'll switch that up. We'll say, actually, let's make the DAI vault, because they are the stablecoin depositors, right? They're probably more risk averse than the Ether depositors. We'll guarantee them a fixed return. We'll give them an X% return, during the epoch, and then if and we'll basically take away from the ETH depositors. If the DAI amount actually reduces, we'll take some money off the ETH depositor side just to make sure we pay off these DAI depositors. But the cool thing is then the ETH depositors, the risky depositors, they will get all of the fees in excess of that, right? So let's say the premium is 2% per month. Cool. If the DAI depositor deposits $100, they're guaranteed to get $100 or $2 back, unless in a very extreme scenario where the liquidity share value goes down significantly. But then the ETH depositors get to keep all of the fees. So they get not only the fees on their position, but the fees on the DAI position, meaning that they effectively get kind of a 2x leverage position. So this is really cool. We created almost like a structured product that allows the fixed side to get a fixed yield, and then the variable side to get almost a 2x leverage position. And now by making this premium more or less attractive, we can control how much capital goes into each of these things. But how do we actually determine that premium, right? Do we just determine it offline? Do we want to have a person that's kind of submitting that premium every month? No, right? The whole point of trustlessness is that we don't want to trust a single person to manage this. We don't want someone to build a spreadsheet and just submit these values. We want to try and automate it. So this is where I think we can really leverage StarkNet and really try and push things forward. So this ultimately becomes a control problem, right? And the control problem is we are in control of this premium, X%. We can bound it in some range, let's say 0 to 10%. You know, it doesn't really make sense to less than 0 because it basically guarantees loss of capital for the senior tranche for the DAI depositors, right? So we'll say 0 to 10%. 10% is a lot per month, so probably don't go above that. Based on the premium, we'll have some response from the user base. We'll have some amount of capital going into each side, and our goal is to maintain the ratio as close as possible to 1. So how do we tackle it? Well, there's this, you know, in control theory, there's a couple different controllers that we can use, but we want to look for ones that have low storage requirements, right? Because we're ultimately trying to put this on chain. And PID controllers are something that looked really interesting. I'm not a control theory expert, but it's fun to dig around. And PID controllers basically only use effectively 3 types of storage. They store basically the error. So for example, if we set a premium to be like 2%, and then we find that the ratio is 0.8, we can call the error 0.2, right? So the first thing it looks at is just the error itself, the size of the error. The second thing it maintains is the change in the error over time, right? Is the error getting smaller or is the error getting bigger? And then the third thing PID controllers look at is the cumulative error, right? And so these 3 terms, they're called the proportional term. Then the cumulative term is the integral term, and the change term is the derivative term. And that's why they're called PID controllers, basically proportional, integral, derivative. So, and basically you just have a coefficient for each of these controllers, and turns out this is how you can build a lot of different systems, like including systems that, you know, control temperature in manufacturing plants and so on, or fly drones. I actually know someone who's tuned PID controllers to fly drones and actually learned a lot from his explanations on how to do it. The kind of main lesson is a lot of trial and error. But in crypto, we want to make it a bit more discrete. So there is kind of a broader theory on discrete controllers. I've simplified it down a bit. Effectively, we're just going to have this, you know, a Python class where we just maintain these 3 coefficients of, you know, how do we correct for proportional error? How do we correct for integral error? How do we correct for derivative error? And you can kind of go in and dive into the math of this, but I'll jump ahead. I'll basically say, you know, there is a tuning process here. So you actually get to kind of figure out, like, you know, how to tune the controller so that it actually achieves the balance required. And there's trade-offs here. You can make it too volatile. You can make it too slow, which is the second one. You can make it quick, but like a little bit too volatile in the beginning. And then you can make it kind of just perfect, where it's like sort of quickly reaches the target value, in this case 100, and then doesn't really oscillate. And so, you know, that's kind of, this is kind of a perfect example of like how you would tune one. And what I did, you know, what makes it kind of actually work in this case is that, you know, how do you really tune it, right? How do we do this exercise when we don't have a million months that we can spend seeing how users react, right? Because in practice, what I would love to do is just to launch this vault, you know, just set random premium values like 5%, 3%, 1%, 2%, and just kind of see what the response is and then tune it over time. But we would have to wait a whole month to get like an actual single observation in this case. So we do have to simulate. We do have to model the system, right? So how can we model the system? Well, I sort of created these 4 different modules that I pieced together. One is just using a simple price curve to predict how Ether prices can evolve, right? And this you can just use simple kind of Brownian motion, very common in stock price modeling. The second thing is I actually wrote the AMM contracts, like a version of the AMM contracts in Python as well, to really implement, you know, how does JediSwap allocate kind of the quantities of the different shares. The third thing is I created a predictive model that basically predicts returns. I mean, all it really does is just takes the price, the Brownian price curve, just runs a bunch of Monte Carlo simulations of that, and then figures out like how much would the senior tranche get, how much would the junior tranche get, what is the premium, and figure out what the returns on both sides are basically. And then finally, I had to create a utility function, which means I had to take a guess on like how users would actually value the different types of return profiles, right? Because it's one thing to be able to predict returns, but it's a whole other thing to say, okay, based on these returns, do you think users would deposit, you know, $1,000, $1 million, $10 million, or absolutely nothing because they don't find it valuable, right? So I made some assumptions there, and that's where really it's more of an art than a science in terms of trying to make these assumptions until you start to see some real world data. But with that all together, I basically could create a simulated scenario, which then I could tune against. And so you see in the final chart here, you see that the kind of orange term is the premium that I'm controlling, and then the blue term is kind of this sort of ratio that starts to the error term that starts to oscillate around 0 as we kind of get more efficient at tuning it. And so this is kind of what it looks in the end. I managed to get a situation where, like, you know, it thinks that a 25% premium kind of annualized is potentially good under kind of the assumptions that I made, right? The cool thing is here that this doesn't mean that we're going to go on and set the premium as 25%. We're really tuning here the actual control mechanism, right, for the premium. Because in the real world, the premium could end up being 0.5%, it could end up being 10%. We don't really care. All we care about is like how this principal controller, this PID controller, is gonna respond to the values of both of those vaults changing. So as an end result, if we put all this together, we should really expect a vault where the predicted premium is going to be stable, and people are going to be encouraged to basically deposit the same amounts and hopefully have a high level of allocation, right? So the kind of insight here is that we are learning off-chain and then we're controlling on-chain, right? We have this custodian, and the custodian is going to maintain this X% premium, and we're going to adjust it epoch by epoch basis, just using very simple kind of three different storage terms for the PID controller. And the choice here is, like, we could actually give the admin some power, and the power we could give the admin is basically to change these proportional terms over time. But even this has some potentially adversarial impact. So I think there's degrees of trustlessness where what we don't want to do is we don't want to allow the admin to set the premium, but we are okay with allowing the admin to maybe control how the premium responds, like how quickly the premium responds to different changes in depositing behavior. So that's kind of an example of why things don't necessarily have to be fully immutable. And then kind of generalizing this, showing you just one other example. We could try and build a trustless yield aggregator as well, where, like, if we have 3 vaults, how do we figure out, like, how much of our capital should go into the vault 1, vault 2, vault 3 automatically, right? Well, again, we go and look for some field in machine learning where people have tackled a similar problem, and we can find, online portfolio selection is a great one. And specifically, again, we look for cases where there is a low storage requirement. And I found this paper called Online Portfolio Selection Using Multiplicative Updates, which claim that it can kind of make these portfolio allocation decisions using only constant storage requirements. And sort of, if you want to dig into that, the formulas here, it's very, very beautiful. The idea is that it only needs to look at the returns from the past epoch of these different vaults, and then it can sort of figure out the optimal weights for the next epoch going forward, just based on the past returns and the past weights from the previous epoch. And it beautifully is able to it has a learning rate parameter that controls how much it's sort of keeping inertia from the previous epoch results, and how much it's really responding to the next to the previous epoch that just happened. And so the idea is that each vault will just report its returns, and then this kind of meta vault or this kind of aggregator vault will really decide on the relative investment amounts. So how do you do these learning techniques? I'd say find a field, look for methods that have minimal storage requirements, modify the methods, simplify them. Compute requirements like complex functions are great. StarkNet can tackle them very well, but storage is really expensive. And then also, don't be afraid to look for methods that have these learning tuning parameters and tune them offline. I think this is a very new way of building protocols and one that we should explore a lot more, both in gaming, in DeFi, and many other places. In conclusion, I think it is possible to build trustless algorithms in areas that currently require a lot of trust in third parties. And I've shown, I think, a thinking process how we can do that. Right? Trustless algorithms offer a very rich design space. Right? This is just one example where you need to use keepers and oracles and off-chain learning to really make this trustless. And I think it's similarly challenging for a lot of things that we currently don't have answers for. I think as another conclusion is ultimately we can hold protocols to a much higher standard around upgradability and discretionary management, right? There's no excuse to say, oh, we need this to be managed because there's no way to do it otherwise. I think there often is, and I think we just have to find it. And with that, thank you for following through, and happy to dive into questions.
Feel free to chat it in the message chat, anyone, if you have any questions or follow-up questions to Peteris, or you can ask on the Q&A section too. So
Okay, so yeah, so first question, are the Yagi keepers decentralized, and what's the incentive to become a keeper? Yeah, those are wonderful question. So right now the keepers are not decentralized, but it's definitely the aim to make them decentralized. Of course, again, sort of to make the overall network trustless. The reason they're not decentralized just yet is actually the second question, which is what's the incentive to become a keeper? Right now, we are not charging task authors for execution. So since we're live on testnet, we actually subsidize all executions right now, or we're trying to do our best to basically do so. There's definitely some contracts that are more expensive than others, but we're doing our best to make it really easy for task authors to get started. And as a result, there's really no incentive for keepers. I mean, even if they were earning some ETH, it would be testnet ETH at the moment. So we don't really have an incentive to attract keepers and keep them involved in the system. Now, we do have a system designed and developed that would be available on mainnet and allow us to actually have this sort of compensation between keepers and task authors. And the idea there is effectively that task authors would pay the keepers for the execution. So whichever keeper actually ended up executing the transaction, the task author would pay them a fee. And of course, the fee would have to come in two parts. The first part is the actual fee for the transaction itself. If it costs X amount of gas, that's what it needs to be covered, of course. But then also some margin above that, right? Because there's probably some, every keeper is running an off-chain process. Maybe they're running it on their own laptop, but probably they're actually running it on some sort of server. And so they're paying for compute costs. So we want to compensate them for that and also give them a little bit of incentive on top of that. So usually there is a margin on top of this underlying gas cost. What makes it really difficult to set this margin right now is that in StarkNet, we do not have the ability to measure transaction costs on chain. So it's on mainnet, we can sort of say, we'll just give a 20% blanket premium. If a transaction, we'll see how much on chain a transaction ends up costing, and we can build into the transaction that it's going to give 20% extra gas to whoever executed that transaction. On StarkNet, we're not able to have that gas metering. I think it's probably a good thing, as it actually creates some important advantages around sort of security and predictability of execution. But it makes it tricky to create an incentive network for keepers. And so we're kind of waiting for future developments. We expect that there may be a development where there's going to be able to designate a subsidy account so that a keeper can say, hey, I'm executing this transaction, but the fee is actually going to be paid by someone else. And so we're openly thinking about mechanisms there. We have a kind of a mechanism that's ready to go, but it's relying on the assumption that each task should have a constant fee. So the mechanism we have right now is where a task author could say, hey, it will cost, I'll pay 20, I'll pay like 20 micro, fractions of ETH, or way, but that can vary per transaction. And it turns out that a lot of tasks, one transaction could cost X amount of ETH, another transaction could cost 5 times more. So we don't want to force task authors to sort of give the highest possible fee when most of the transactions are going to be cheaper. What we actually want is to really, task authors have to pay really the minimal amount just based on the actual gas that was consumed. And there's just currently no good way to do that. So we're holding off on mainnet until then, and we'll have an intermediary solution. But I think in the long term, there's probably going to be this sort of fee master, pay master approach that we can incorporate. And then once we start paying the keepers, we already have a number of companies interested in actually running these keepers. Then it becomes straightforward. There's a financial incentive, and we can make it much more decentralized, right? By actually then also decentralizing the process of which the keepers are elected and selected, and by making it permissionless. There's sort of a broader design space on how you kind of manage keeper reputation and so on, which I could dive into at length. But it's a fun challenge. I mean, there's issues of reputation, of like how you disincentivize keepers to submit or to not submit, right? When it's useful for them to do so. There's issues of keepers not wanting to maybe maintain tasks that don't have a lot of fees, right? So how do you incentivize tasks that have lower fees to just really get attention? There's issues around gas auctions, where like if you allow 100 keepers to sort of attack, to kind of try and execute the same task, what if they end up just bidding the gas higher until it's not profitable for any keeper to execute a task? So you can start thinking about how to allocate positions of execution and so on. You have this issue of like, well, if you just whitelist all the keepers, well, is it really decentralized if you just whitelist 20 different keepers? Or does it become decentralized when anybody can become a keeper robustly? So yeah, those are wonderful questions, but our first focus is going to be on really putting those fees in place, and then starting with a really trusted set of keepers, and then kind of adding more decentralization as we go on. Yeah, I think that's a great example of where, ultimately, if these keepers are used as part of a trustless application, you can't fully call it trustless until the underlying components and dependencies are fully trustless, right? But obviously, we're talking here about building things, on testnet with the aim of eventually becoming trustless, right? So obviously there's going to be a transition phase with a lot of protocols out there. It's not uncommon, I think, for most protocols on StarkNet right now to actually have some upgradability, some admin accounts. And it doesn't really mean that they're not striving for trustlessness. I think it just means that they're sort of bootstrapping the protocol from scratch. So as long as their intentions in the long term are towards trustlessness, I think it's okay to build on top of these protocols and keep iterating there. And we've definitely done so as well, even in terms of vaults. Not every protocol we're going to build upon at this stage is going to be sort of fully trustless, and that's completely fine, I think, in a design stage.
Great. We'll open up for final one or two questions for the sessions. If anyone has more questions, feel free to chat it in the uh, Q&A section or in the chat section. Both should be open right now. So yeah.
Oh, so I think we have another question in the chat, which is, where does the name Yagi come from and what does it mean? Yeah, so the true answer to this is that it comes from, maybe the less inspiring answer is that it comes from a very active domain search for kind of four-letter .fi and .finance domain names, and like some filtering tactics there. But I think it also connects nicely with actually what we're trying to do. So Yagi actually stands for yield aggregation and generation infrastructure. So sort of the idea was always to really work up towards providing infrastructure for yield aggregation, starting with the keepers and then actually building the vault. So I think it connects well with actually that abbreviation of the name. But yeah, I wanted to have a really short and succinct and distinctive name that had a .fi domain. So not a lot of those left, unfortunately. So I'm sure somebody has to come up with a new, more modern domain utility.
Great. I think, oh, there's one more question.
Okay, Matthew's asking, of all the components you described, which do you feel is the hardest to make trustless or in the earliest stages of being made trustless? Yeah, I mean, that's a great question. I think they're like, there's different degrees of difficulty, right? There's like the question of like how long it will take to really have them fully trustless. I think the bigger risk there is with some of the dependencies that we have. It's easier to make a bad trustless approach that kind of works but is fully trustless, right? It's really hard to make a trustless Oracle product, right? And so I think Empiric team is like incredibly talented team and well positioned to do it. But I think in the market today, I don't think we have any trustless oracles. And so it'll be, I think that's a real challenge for them to build a trustless oracle. There's this other side of like quality, right? And that's where I think the sort of premium tuning part and the off-chain learning, I think there's just so much to discover there, where the algorithm I presented today with kind of optimal control is a very early take, right? And I'm definitely not a control theory expert. And so this is kind of a very early take, and we'll just have to see when this vault actually launches on mainnet, how it goes and how it works, and just keep tuning it. And so I think that will also take time, right? I mean, if we launch one vault on mainnet, we get 12 iterations over a year. So hopefully we launch a couple more vaults in parallel. The more liquidity pools there are, the more vaults we can ultimately launch and sort of just get more and build up more training insights. So I think that also takes time. So it really, maybe the honest answer here is there's no easy component to this, and they're all for various, have various degrees of difficulty, right? But it's still worth trying, and it's still, I think, really fun to keep discovering kind of what trustless design can be for some of these more sophisticated things, right? It's very easy to build a trustless AMM. It's very easy to build a trustless kind of NFT exchange. I think it's really hard to take a product that exists in traditional finance and make it a trustless crypto product. But I think it's really rewarding to try and to get there. One more quick question, which is how long before we go live or reach launch on live? So yeah, so in terms of this particular vault, it's already deployed on testnet at a first generation version. kind of one of the very early versions, not with the Oracle integration and all that. So I think that'll take a couple of months to get to this final iteration. I think in terms of the Keeper network, we're a little bit dependent on ultimately customers. Like if there's customers that want to go on mainnet, we'll get there and figure out a way to work, even if it's temporarily not trustless. In terms of like getting a fully trustless version on mainnet, I think there's dependencies outside of our control, which is basically the network design. We want to see what the final design of the network looks like, what the final version of account abstraction looks like before we commit to a design on mainnet. So we're not in a rush there until there's a customer pool. But yeah, with these vaults, pushing them as quickly as we can. So I expect more on that soon.
Great. Thanks a lot for your time, Peteris. I think this is our session 7. And for everyone who's trying to participate for the hackathon, there will be attendance at our Discord channel. So please help filling it out. And again, everyone, thanks a lot for participating. And also thanks huge to Peteris for coming and discussing about Yagi Finance to everyone.
My pleasure. It's been awesome. Thanks everyone for joining and following along. And yeah, if you have more questions, definitely please feel free to follow. Always happy to chat about this stuff.
Wonderful. Thanks a lot, everyone. Have a good day.
Thanks a lot.